All right, thanks for joining me again. Sorry to go a little over today, but I do want to make sure you see these 3 examples for tomorrow's class. I got one more substitution here that I want to show you, and this is on equations that are called Bernoulli equations. So Bernoulli equations are going to show up in this form. It almost looks like a regular linear equation, except you've got this extra y to the n term, or the dependent variable to the n term, on this other side. So when you see that you have a differential equation in this format, you're going to make the substitution v equals y to the 1 minus n. So let's go ahead and talk about how that works through an example. In this first example, I'm going to just kind of make a note of what's what here. We've got p of x is going to be negative 5, and q of x is going to be negative 5 over 2x. And that y to the n that's new for us here is going to become y to the n equals, that's the y cubed here, so that's going to be y to the third. So n is going to be 3 in this example. All right, so then where do we go from there? I'm going to start off by making that substitution. I'm going to let v equal y to the 1 minus 3, which of course is y to the negative second. So here's the sort of trick in this equation. You're looking at the equation and maybe thinking to yourself, I don't see y to the negative second. That's not anywhere in the equation. So what the heck do I do with this v? Well, we're going to make a y to the negative second in the equation. We're going to get that in there so that we can make that substitution. So think about algebraically, how can I get y to the negative second into the differential equation here? I think perhaps the best way to think about this is ask yourself, okay, if I have this y term here, what would I need to multiply that by so that it became y to the negative second? And then multiply the entire equation. You can do that as long as you do it to the entire equation by whatever that term is. So notice that if you multiply everything by y to the negative third on both sides, this term in particular will become y to the negative second, and that will allow me to make that substitution. So my new equation, my transformed equation, is going to be called y to the negative third dy dx minus 5 times y to the negative second equals negative 5 over 2x, and then if I'm multiplying by y to the negative third, this y will zero out. So this is going to be my new transformed equation. So let's go ahead and make some substitutions. Now, as always, I need to take a derivative because I need to get that dy dx in there somehow. So let's come back here. We said, remember, v was equal to y to the negative second. So then use implicit differentiation to find dv dx. So the derivative of this expression with respect to x, that's going to be negative 2 y to the negative third times dy dx, which becomes, if we solve for dy dx, we end up with negative 1 over 2y to the negative third dv dx equals dy dx. All right, so that's going to be our substitution. Notice that dy dx, whoops, let me get rid of that, dy dx, let me write that again, is what's going to get substituted in here in this part of the equation, and then v, of course, is going to replace the y to the negative second right there. So let's rewrite our new equation. So our new equation now is going to look like this. We're going to have y to the negative third times negative 1 over 2y to the negative third times dv dx minus 5v equals negative 5 over 2x. Notice this time that these y to the thirds cancel out, and I have negative 1/2 dv dx minus 5v equals negative 5 over 2x. And this doesn't give us something that is separable, but it does give us a regular linear first order differential equation, and I can use the integrating factor to solve this from here. I'm going to get rid of this negative 1/2. I'm going to multiply everything by negative 2. So my equation becomes dv dx plus 10v equals positive 5x on the other side. Then my integrating factor will be e to the integral of just 10 dx, which will give me e to the 10x. So now multiply everything through by e to the 10x. So let me make a note here. This is mu, just in case you look at it later and you're wondering what that was. Make a note that that's your integrating factor. Okay. And then, so multiply everything through. Go ahead and pause the video. Multiply everything through by e to the 10x. And then check and make sure you get the same thing that I have. And then, of course, this left side, as usual, is the expanded product rule of, so it's the derivative of v and e to the 10x, right? The derivative of e to the 10x would be 10e to the 10x. So this is the derivative of e to the 10x times v. And that's equal to e to the 10x times 5x. So if we integrate both sides now, we get e to the 10x times v equals, now here's the fun part, and I'm going to skip the details of this for now, but the integral of e to the 10x 5x would require integration by parts. So I've already worked it out. Let me just tell you what that is for time's sake. We don't have to go through all the details here, but I am getting, let's see, I've got x over 2 e to the 10x minus 1 over 20, I believe, e to the 10x plus c. And then if you divide everything through by e to the 10x, those will cancel out. So you end up with v equals x over 2 minus 1 over 20 plus c over e to the 10x. And then remember, of course, we have to replace v with what we were setting it equal to. Don't forget, v was equal to y to the negative second. So then my final answer, I'm going to come back up here, and I'm going to write it up here somewhere. My final answer becomes y to the negative second equals x over 2 minus 1 over 20 plus, and I'm short on space here, so I'm going to write this as c e to the negative 10x, so I don't have to deal with another denominator. Whew, there we go. So that is solving when you have an equation that looks like what's called a Bernoulli's equation. All right, and we'll do some practice with these in class. I know this is a lot of information here, so hang in there. Just make sure you bring your notes with you, and we will do plenty of practice and work on recognizing these different types of equations in class. So I'll see you then.